In the previous video, we built our generic register module that lets us implement the various registers in our CPU. Now we're going to build our ALU as shown in our computer architecture diagram. I've created a quarters project called SAP-ALU and have created a Verilog module called SAP-ALU top.v. I've set this module as a top module in this project. SAP-ALU top.v is very similar to the top module called SAP register top.v that we had in the project in the previous video. The only thing I've changed is that I've added two instances of the generic register module and named them A register and B register. These are the A and B registers that appear in our computer architecture diagram. Before we start on our ALU, I mentioned in the previous video that I'd show you how to handle inputs and outputs if you don't have enough switches or indicators on your particular FPGA board. Even with all the input and output resources on the FPGA development board that I'm using, as the design becomes more complex, it's advantageous to have a way to probe your design easily. Quarters Prime has something called In-System Sources and Probes in its debugging IP library. The In-System Sources and Probes editor allows you to read data from and write data to the design on the FPGA with a JTAG interface. We can use the In-System Sources and Probes editor to debug our design and for monitoring the various registers and flags within our CPU. Xilinx has a similar IP in its Vivado design suite called Virtual Input Output or VIO. It works in a very similar way if you're using a Xilinx FPGA or development board. I'll talk about it a little bit later in this video. Here I'm going to find the In-System Sources and Probes IP in the IP library under Simulation, Debug, and Verification, and then select Debug and Performance. Now if I double-click on the In-System Sources and Probes, the Platform Designer window opens and asks me for an entity name, which I enter as Virtual I/O 8-bit. This is the name of the Sources and Probes module that the Platform Designer will create for us. In probe parameters, I set the probe port width to 8 bits. You can select from 0 to 512 bits wide probe ports. In the sources parameters, I also set the source port width to 8 bits. I click on Finish and the Platform Designer creates the files for our project. Once the Platform Designer window closes, you'll get a message that you must manually add various files to your quarters project. Now I add the files that were generated to our project. If I open Virtual I/O 8-bit.v, you can see that it instantiates a module called Alt Source Probe Top, which I've also added to our project. Now I'm going to create an instance of our Virtual 8-bit I/O module in our SAP-ALU top file. Note that the probe port is an input and the source port is an output. Both are 8 bits wide. We will name this first instance VIO WBus, and the names will make sense in a little bit. Next, I'm going to add 3 more instances with the names VIO Control, VIO A-Reg, and VIO B-Reg. With our VIO WBus instance, I'm going to connect the probe port to our WBus, which is 8 bits wide. The VIO A-Reg port is connected to our 8-bit wide A-Reg out port of our A register instance. The VIO B-Reg port is connected to the B-Reg out port of our B register instance. In our VIO WBus instance, we're going to connect the source port to an 8-bit wide wire we will call WValueIn. To write to our A and B registers, we need to be able to drive a value onto the WBus. In the previous video, we used switches 0 through 7 to do this. Since we're not going to use physical switches, we'll need a way to drive a value onto the WBus, and the WValueIn wire will do this. You'll see how in a minute. For the VIO control instance, we'll connect the source port to an 8-bit wide wire called control. For now, we'll not connect the probe port of the VIO control instance. We'll connect the VIO A-Reg instance to an 8-bit wide wire called A control. With the VIO B-Reg instance, we'll connect the source port to an 8-bit wide wire called B control. Previously, we used 4 key buttons on the FPGA development board to control our clock pulse, reset, and the A latch and A enable signals. I'm going to comment these out since we won't be using physical push buttons in this video. I've already added our 8-bit wide WVal in wire in our declaration sections in our Verilog file. Here I'm adding the 8-bit wide control wire to our design, as well as the A control and B control wires. You can see that these are all the signals that we have connected to our virtual I/O 8-bit modules. The VIO control instance will serve as the replacements for our physical switches on the development board. Here I'm going to create a signal called W-enable and assign it to control bit 0. The W-enable signal will allow us to drive the W bus with the value that we send to the WVal in that is connected to our VIO W bus instance. Next, I'll connect our reset wire to control bit 3. I'm reserving control bit 1 and control bit 2 for future use. And I'm connecting our button wire to control bit 4. Remember that our button wire, when asserted, will cause our clock pulser module to output a single clock pulse each time the button wire is pushed. Maybe button was not a good name for this. I could have named it trigger or one clock pulse or something like that. For now, I'll leave the name as button. I'm going to connect our A latch control signal to bit 0 of the A control wire. Remember, the 8-bit A control wire is connected to our source port of our VIO A-reg instance. Likewise, I'm going to connect our A enable control signal to bit 1 of the A control wire. Bits 2 through 7 of the VIO A-reg source port are unused. We'll do the same thing for the B latch and B enable control signals. Previously, we used switches 0 through 7 to drive our W bus when the A enable signal was asserted. This is when we were testing our generic register module in the previous video. I now have a control signal called W enable. If asserted, the value we have on the WVal in wire, which is connected to the source port of the VIO W bus instance, will be driven on the W bus. When W enable is not asserted, the W bus will be set to high impedance. Now we can probe our registers and the W bus as well as control our latch and enable signals from the virtual inputs and outputs. We're ready to test it. I'll compile and then program the FPGA. Now that the FPGA is programmed, we can open the In-System Sources and Probes editor, which is in the Tools menu in Quartus Prime. The System Sources and Probe editor is open. The first thing we need to do is configure the JTAG chain by selecting the USB blaster on the FPGA development board. Next, I right-click in the Probes and Sources Instances table and select Recreate Instances from JTAG Device. When I do this, it groups the various source and probe signals together. Depending on what you're doing, you can capture a variable amount of samples to display. Besides being displayed, they're also written to an event log if Save to Data to Event Log is checked. Because of what we're using this for, that is replacing physical keys, switches, and displays, I usually set this to 0, which makes it easier to see what's going on. You can see that there are 4 instances of the sources and probes, and this corresponds to the 4 instances in our design file. They are assigned an index number, and they appear in the order that they were instantiated in the Verilog file. The first instance with index 0 is our VIO WBus instance. Let's rename the probe and source names to something descriptive of what they do in our design. So for the probe port of our VIO WBus instance, we'll rename to WBus. The source port we will rename to WVal in to correspond to what is in our design file. We'll set both ports to display their values in hexadecimal format. With the VIO control instance, we'll not be using the probe port, so I'll rename that to unused. I'll set the unused port to display in hex format also. In the VIO AREG instance, we'll rename the probe port to AREG. This will display the contents of our A register. We select hex format for the AREG port. In the VIO BREG instance, we'll rename the probe port to BREG, and this will display the contents of our B register. We then select hex format for our BREG port. Next, I'll select the source port of our VIO control instance, right-click, and then select Ungroup. You can see that our W enable signal is connected to control bit 0. So if I double-click on the source 0 name here, I can change that bit's name to W enable. Our reset signal is connected to control bit 3, so we rename source 3 to reset. And our button signal, which pulses our clock, is connected to control bit 4, so I rename source bit 4 to clock pulse to denote that as the one-shot clock pulser. I'm going to group the unused bits by first selecting them and then right-clicking and selecting Group. I'll rename these unused bits to Unused. Now I'll group the source port of the VIO AREG instance. Bit 0 of our AREG control is connected to A latch. Bit 1 is connected to A enable, so I rename it to A enable. I'll group together the unused bits and rename them to Unused. I do the exact same thing to the VIO BREG instance. Now the signals are named with useful names that we can relate to in our design. We should save this file so we don't have to recreate it each time we open the editor. Now that we have it saved, let's start all 4 instances. To do this, we select all 4 instances, and while making sure they are selected, we click on the Continuously Read Probe Data button. Also notice that we have write source data set to continuously. This means that anytime we change the source data in the editor, it will be sent to the FPGA. Otherwise, if you set this to manual, you have to click on the send button to update the FPGA. Now that the probe data is being sampled, we can use this to control and update our registers in WBus. First thing I'll do is do a reset. Next, I need to pulse the clock, so I click on the clock pulse signal to pulse the clock once and to reset our registers to a known state, which in this case is 0. Let's write the value of 2 hex to our A register. I enter the value 2 in the WVAL-in port. Notice that the WBus is still showing FF hex, so we're not yet driving 2 hex onto the WBus. To do this, we need to assert the W enable signal. You can see now that 2 hex is being driven on the WBus. To write this into the A register, we have to assert the A latch signal. Then we have to pulse the clock. We do this by toggling the clock pulse signal. You can see that the A register now contains the value 2 hex. We deassert the W enable and the A latch signals. If I assert the A enable signal, you can see that the A register drives its contents, which in this case is 2 hex, onto the WBus. When I deassert the A enable signal, the WBus goes back to the high impedance state. Now let's write 5 hex to the B register. We enter 5 hex in the WVAL-in source port. Next, we need to assert the W enable signal to drive 5 hex onto the WBus. We can see that the WBus is showing 5 hex. We assert the B latch signal and then we toggle the clock pulse signal. The value of 5 hex is latched into the B register. If we assert the B enable signal, the B register drives 5 hex onto the WBus. Let's move the value in the B register, which is 5 hex, into the A register. We can do this by asserting B enable and A latch. You can see that the value of the B register, which is 5 hex, is being driven on the WBus. If we pulse the clock, you'll see that 5 hex is written to the A register. Now both the A register and the B register contain the value 5 hex. I'm going to reset the registers by asserting the reset signal and pulsing the clock. You can see that the registers are reset to 0. We can stop the sampling by clicking on the stop button. Before we close the editor, I'll save this file once more. Okay, now that we have a way to read and write values to our FPGA over JTAG, we can move on to creating our ALU module. I'm going to create a new Verilog file and name it SAP-ALU.v. I'll then add that file to our project. We create a module called SAP-ALU. From the architectural diagram, we see that we need 2 8-bit wide inputs, one for our A register and one for our B register. We also need an 8-bit data port, which we declare as in-out. This port connects to the WBus. We need an enable input and a subtraction input. When subtraction is asserted, the ALU subtracts instead of adds. I'm also going to add 2 outputs, one called C and one called Z. These will be our carry and 0 flags, which we'll discuss and use later. As always, I create a commented out instantiation template for our module that we can cut and paste into other modules. The ALU is actually pretty simple to implement. I'm going to declare a 9-bit wire called ALU plus and assign it to AREG data plus BREG data. That's all there is to addition. The ALU plus register is a 9-bit register. When the ALU adds the A and B register inputs, the result may overflow. In other words, the result cannot be represented with 8 bits. An example of this would be adding the value FE hex held in the A register to the value 3 hex held in the B register. The result cannot be represented with 8 bits. When this happens, we need an indication that this is the case. The 9th bit in ALU plus is our carry bit. It will be a 1 or high if there is a carry on our addition operation. Next, we'll declare a 9-bit wire called ALU minus and assign that to the subtraction of register B from register A. The 9th bit in ALU minus is our borrow bit. It indicates that a borrow occurred on subtraction. An example of this would be if register B held the value FE hex and register A held the value 3 hex. So the subtraction would be the A register, which is 3 hex, minus the B register, which is FE hex. I declare an 8-bit wire called ALU result. This is the 8-bit result of either our addition or subtraction. If the subtraction input is asserted, we'll want the ALU result to be 8 bits of the ALU minus result. If the subtraction input is not asserted, ALU result is 8 bits of the ALU plus result. ALU minus and ALU plus are 9-bit registers. The 9th bit contains the carry bit in the case of addition or the borrow bit in case of subtraction. In Verilog, the curly brackets denote concatenation. Since the C or carry output is 1 bit wide and the ALU result is 8 bits wide, we can concatenate these two signals where ALU result gets the bottom 8 bits of ALU plus or ALU minus, and C gets the 9th bit of ALU minus or ALU plus. For the Z or 0 flag output, we want it to be set or high when the ALU result is 0. So here we assign the Z output as 1 if the concatenation of the C bit with the ALU result is equal to decimal 0 represented with 9 bits. The Z output is 0 when the concatenation of the C bit and the ALU result is not equal to 0. Now that's it for the ALU. I'll grab the instantiation template and copy it to the top module. I uncomment it and start connecting ports of the ALU module. So the AREG data and BREG data ports are connected to AREG out and BREG out respectively. The data port is connected to the W bus. I'll declare a control signal called ALU enable and connect it to the enable port. Likewise, I declare an ALU subtract signal and connect it to the sub port of our ALU module instance. I'm going to declare ALU-C and ALU-Z signals and connect them to our module C and Z ports. We will assign the ALU enable to control bit 1 and ALU subtract to control bit 2. I'm going to assign the ALU 0 flag to the red LED on my development board. I'll assign the ALU carry to the red LED 1 on my board. In our VIO control instance, we did not connect the probe input to anything. What Quartus Primes does in this instance is assign all bits of the unconnected ports to ground or zeros. If you don't want that behavior, you need to explicitly set the port to some value, such as FF hex, for example. I want to be able to read the C and Z flags, so I'll assign the ALU Z flag to bit 0 of our VIO control port and assign the ALU C flag to bit 1 of our probe port. That leaves 6 bits unused. So I concatenate 6 0 bits with the C and Z bits like this, and that makes 8 bits total. Let's compile and program the FPGA. I'm going to double-click on the previous saved SPF file to open the in-system sources and probes editor window. I select all 4 instances and then click on the continuously read button. I'm going to reset everything by asserting reset and pulsing the clock. Actually, let's add the control signals ALU enable and ALU subtraction by ungrouping and then renaming their respective bits. Bit 1 of control is the ALU enable, and bit 2 of control is our ALU subtraction. Also, we'll rename the probe port to flags and set the data display type to binary. Since we reset the A and B registers, they both hold the value 0, so you can see that the 0 bit is set in flags. You can also see that red LED 0 is on, which represents the 0 flag. Now I'll write the value FE hex into the A register and the value 3 hex into the B register. It looks like we now have our C flag working. FE hex plus 3 hex is the value 1 hex plus a carry. If we subtract, we get the value FB hex, which is the A register, which holds the value FE hex, minus the B register, which holds the value 3 hex. Maybe we want to transfer the ALU addition result into the A register. We do that by making sure that ALU enable signal is asserted along with the A latch signal. Pulsing the clock transfers the value 1 hex into the A register. If we want to look at the addition, we assert ALU enable again, and we can see that 4 hex shows up on the W bus, which is correct. If we want to see the result of the subtraction, we can assert the ALU sub signal with the ALU enable signal also asserted. The result is FE hex with a carry bit set, or in the case of subtraction, it's actually the borrow bit. The A register contains 1 hex and the B register contains 3 hex. 1 hex minus 3 hex is FE hex with a borrow. Let's transfer the result of the addition of 1 hex plus 3 hex into the A register, which currently holds the value 1 hex. We assert the A latch and the ALU enable, then pulse the clock. You can see that the result of the addition was transferred to the A register. If we assert ALU enable, we see that the result is now 7 hex. If we write the value 3 hex into the A register and assert the ALU enable and ALU subtract signals, the result is 0, and you can see that the 0 flag is on, which is as it should be. Lastly, I assert reset and pulse the clock, which resets both registers to 0. I mentioned earlier that if you're using a Xilinx FPGA, that Vivado has an equivalent of the in-system sources and probes IP. Xilinx calls it VIO, or Virtual Input Output. You can find it in the IP catalog in Vivado under Debug and Verification. If you double-click VIO, a customized form will open. With the in-system sources and probes IP in Quartus, I had to create multiple instances of the module, each one with an 8-bit probe port and an 8-bit source port. In Vivado, the VIO IP allows you to have from 0 to 256 probe and source ports. You can set the probe port, which Xilinx calls an input probe, to a width from 1 bit up to 256 bits. You can also set the source port, which Xilinx calls an output probe, to a width of 1 to 256 bits. In Vivado, I could have set the probe count to 4 and set each probe to 8 bits. I would only have to have 1 instance of the VIO module instead of 4 instances of the in-system sources and probe modules that I had in Quartus. Otherwise, they work pretty much the same. In Quartus Prime, besides the in-system sources and probes IP, they also have the signal tap logic analyzer. With signal tap, there's no input to your design, so you cannot use it like we used the in-system sources and probes as a kind of virtual control panel. However, with signal tap, among other things, you can have triggers that start the data acquisition when something happens, such as a level change, a rising or falling edge, or a certain value. If you have room in your FPGA, you can use both the in-system sources and probes IP along with signal tap and have both running at the same time. To add signal tap, you need to open the signal tap logic analyzer in the tools menu in Quartus. Once you click on it, the signal tap window opens. The first thing you need to do is add the signals you want to monitor in your design. There are a multitude of options, and this video does not cover even a fraction of them for the signal tap configuration. With that said, if you select the Setup tab and then right-click in the Signals window, a Node Finder window opens up. Here I select Signal Tap Presynthesis as the filter and then click on List. You can add the nodes that you want to monitor. Here I'm adding some of the nodes of interest. When I close the Node Finder window, you can see that the nodes are shown in the Setup window. You can set triggers for each of the nodes. You also have to set the clock configuration. If you don't, you'll get an error. Setting the clock configuration is the same as using Node Finder. I select clock 50. That is what the clock is derived from on my FPGA development board. I'm setting the trigger to the 1 clock pulse node and setting the trigger condition to rising edge. If you're using more than one trigger, you can have various options such as ANDing them together, ORing them together, or setting some other conditions for triggering. Here I'm setting one trigger and it'll trigger on the rising edge of the signal. I'll save the signal tap file and then recompile. Once compilation completes successfully, I program the FPGA. Now I open both signal tap and the in-system sources and probe windows. If I pulse the clock as before, you can see that the signal tap analyzer is triggered. 0 indicates the trigger point. Negative numbers are clock cycles before the trigger, and positive numbers are after the trigger happened. You can configure how many data points are captured in signal tap. Each number represents a clock cycle, and that's based on what clock I have set in the signal tap configuration. I'm using the 50 MHz clock here. You can see the output of the clock pulsar module here. It is one single clock pulse. This is what signal tap is nice for, capturing things like this. With the in-system sources and probes, I could not show you that single clock pulse because there's no trigger conditions with that IP. It just continuously updates, in this case 9 samples per second. Because I could set trigger conditions in signal tap, I can show you the single clock pulse easily. You can see that I can input values in the in-system sources and probes editor and toggle control lines, and the results can be seen in signal tap, such as what the registers contain at certain clock times. You can also move the signals around in signal tap as well as system sources and probes to suit you. Here I've dragged the clock pulsar node to the top of the window in signal tap. I wanted to say a bit more about our ALU module. We could have built our ALU as a ripple carry adder by chaining together full adders. To do subtraction, we would just need to invert one of the two inputs to the full adder and then use the first stage carry in to add 1. We could have just written a full adder module in Verilog like the one I'm showing here, and then use multiple instances of that module to implement a ripple carry adder as shown in this top.v Verilog file. It'll work perfectly fine, and if you really want to understand adders, you can play with it, but I'd rather let the compiler take care of it for us. You'll see how nice that is when we add multiplication and division to our ALU. In upcoming videos, we'll be implementing the rest of our computer architecture. Once we have a running SAP-1 computer in the FPGA, we can then start modifying the architecture by adding to it to make it much more useful. We'll be adding much more memory, new instructions, and new registers as a few examples, and we'll even be writing an assembler for our modified computer. If you like these types of videos, please consider subscribing to my channel, and click on the bell icon to be notified when I release a new video. Thanks for watching, and I'll see you next time.